Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into a fascinating paper, Towards an API for the Real Numbers. It tackles the surprisingly tricky problem of representing real numbers accurately in computer systems, especially when dealing with user-facing applications.
Right. I've always found the limitations of floating-point arithmetic frustrating. It's great for many applications, but it falls short when accuracy is paramount, and the results are directly presented to users who aren't floating-point experts. What's the core argument of this paper?
Exactly. The paper argues that while floating point is great for speed in performance-sensitive applications, it often leads to results that look like bugs to the average user. Think of a calculator displaying 0.7999999 instead of 0.8. That's a classic example. The author proposes a new API for a real number type that aims for accuracy and mathematical correctness, even if it means sacrificing some speed.
So they're aiming for a more mathematically faithful representation of real numbers, prioritizing accuracy over raw computational speed? That's a bold move. What kind of approach do they take?
They build upon the concept of recursive real arithmetic, which represents a real number as a function that computes a rational approximation to any desired precision. But a key problem with recursive reals is that deciding whether two numbers are exactly equal is undecidable. It might never finish. That's a big hurdle.
I see. So how do they address that undecidability problem? That sounds like a major roadblock.
That's the clever part. They don't completely solve it, but they develop a system that provides decidable equality in many common cases. They leverage classical number theory results to create a set of decision procedures that work surprisingly well for numbers computed using standard calculator operations: addition, subtraction, multiplication, division, square roots, trigonometric functions, exponentials, and logarithms.
Interesting. So it's a best effort approach to decidability. They don't guarantee decidability in all cases, but they cover the most frequently encountered scenarios where users expect exact comparisons. What are some of the applications they highlight?
Absolutely. Two main applications are highlighted. First, a calculator application. Imagine a calculator that always displays correctly rounded results, showing exact values when possible, and avoiding those annoying trailing zeros. Second, testing floating point functions. Their real number type can serve as a ground truth for verifying the accuracy of floating point implementations.
That's a really neat application for testing. It's much cleaner than relying on approximate comparisons with higher precision floating point, which can still be prone to errors. What about the implementation details? How do they achieve this?
Their implementation is surprisingly elegant. They represent a real number using three components: a bounded rational factor, a recursive real factor, and a property. The property component holds symbolic information about the recursive real factor, allowing for efficient comparisons and simplifications. They have a really interesting system of tags to identify the type of the recursive real factor, which helps in determining comparability.
So the property acts as a kind of shortcut, allowing them to avoid lengthy computations in many cases? That's a smart way to optimize for speed where possible. What about performance? How does this approach compare to standard floating-point arithmetic?
It's significantly slower, of course. Orders of magnitude slower, in fact. But for the target applications, calculators and testing, the performance overhead is acceptable. They provide some benchmark results showing that even complex calculations can be performed in a reasonable time frame, often under a millisecond for individual operations. They also discuss optimizations, like divide and conquer algorithms for summing large series, to mitigate the performance impact.
That makes sense. The trade-off between speed and accuracy is a crucial consideration here. It seems like they've struck a good balance for their intended use cases. Any final thoughts?
This paper is a really impressive piece of work. It demonstrates that it's possible to build a practical, useful system for representing real numbers that's much more mathematically sound than standard floating point, while still maintaining acceptable performance for many applications. It's a great example of how careful design and clever algorithms can overcome seemingly intractable problems. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and goodbye.
Bye-bye.